And I'm going to do a little bit of a quick review of what we talked about last time. So we're talking about neural networks, of course. And so I'll just sort of scroll quickly through. So here we created a neural network that does the XOR of two half spaces. And so it ended up looking kind of, so these are the basic parts, and then you can put them all together in one big network like this. And then, so here's the terminology that's important. So it comes in layers. Layer 0 is the input layer, and the last layer is the output layer, and we call these in between the hidden layers. So also all neural networks are just big complicated functions involving plus, times, minus, and the activation function. In this example, the activation function is the sign function. And that sort of like decides whether or not the neuron is going to fire. And so this works not just for XOR, but for any logical combination of half spaces. And that's pretty powerful. It means you can do really complex target functions just as a neural network with 3 layers, 2 hidden layers. Okay, so you can't optimize the multi-layer perceptron easily because the sign function is sort of all or nothing. So it becomes an NP-complete optimization problem. So you want to soften the transition function so that you can do some kind of gradient descent. And the book uses hyperbolic tangent, and that's what we're gonna do. So that works well for lots of reasons. One reason is that it, and it nicely approximates the sign function, and you can make it approximated as much as, as clearly as well as you want, which isn't necessarily a good idea because remember the sign function doesn't work well. So but you can make the hyperbolic tangent function approach the sign function if you want to. There are some other options. I'll talk about these more later. So these were important in the deep learning revolution. We'll get around when we do backpropagation and train a network. We'll see some things that go wrong with the configuration from the book and how some tricks can fix some of those issues. The difference between traditional neural networks and deep neural networks is there's a lot of stuff, but really it's just a different way to initiate. You can get a much better deep neural network if you just initialize the weights in a smart way, which people amazingly didn't consider until like the 2010s. And you can also, instead of using like a sigmoidal activation function like hyperbolic tangent, you use one of these others. Then if you do those two things, then neural networks work much better with many layers. Okay, so this is just the general terminology. So each node has a transition function or an activation function. The last node, if you're doing classification, then it has an activation function. But if you're doing regression, then you might want to leave off the last activation function, and then the output will just be a weighted sum of these inputs. Okay, so this is a feed-forward architecture. Each layer has a bias node. The bias node is this 1 at the top. So the 1 has outputs but no inputs. Blah, blah, blah. Okay, so here's the notation. So we were talking about this at the end of class last time. So little l is going to be the notation for the layer that we're talking about. And each layer has DL nodes, and that does not count the bias node. So if you have a layer that looks like, watch this not work. So here's the bias node, and then you have a node, and then a node, and a node. DL in this case would be equal to 3, not 4, because you don't count the bias node. Okay. And these nodes are numbered. So the bias node will be the 0th one. This will be 1, 2, 3. And so the last one has index DL. Okay. So the architecture of the network is just the choice of the sizes of each layer. So that says, you have so many nodes in the first layer, so many nodes in the second layer, so many nodes in the third layer, and then the last layer. So the number of layers and the number of nodes in each layer almost determine everything about the network. Of course, you have to also say what the activation function is and whether or not you're doing regression or classification. So aside from that, so that kind of specifies the hypothesis class, and then a particular neural network involves the actual values that you end up deciding on for all of these weights. So it has lots of parameters, like linear regression, we have like one parameter for each input variable, but we have a lot more parameters than that, even in the first layer now. We have like, for each input variable, we have as many weights just in the first layer as there are nodes in the second layer. So parameters are much more numerous than inputs in a neural network. Okay, so now we're heading towards describing the algorithm that runs a neural network. And so we need to keep fixing this notation here. So if you have node I and layer L-1, that's what this guy is, then we call its output xi L-1. That's the same value that goes out on all of its connections. The weight of the connection from node I and layer L-1 to node J and layer L is called Wij. The inputs to the jth node in layer L is Sj. So Sj is actually applied after they're all summed up. So this diagram is a little bit misleading because it seems like just the value on this wire is Sj, but that's not true. To get Sj, you take all of the inputs and then sum them up. And then to get the output for the next layer, you apply the activation function to Sj. And then that goes out on every single wire and it just repeats. Okay. So here's the actual formula for the input to node J and layer L. It's this, and you can just recognize this as a dot product of two vectors. One of the vectors is this thing, x L-1. And the other thing that's being dotted in here is if you just let I vary with a fixed j, that gives you a vector of weights, and this will be like a certain row of a certain matrix, which will be WL transpose.
All those XL-1s, those are still the inputs?
No, no. So now, yeah. So the inputs have a 0 subscript here. No, wait, sorry. The inputs have a 0 subscript here. So x1, x2 like this, and then x00, which will just be 1. This will be like what we normally call x bar, just the input vector. Okay. So yeah, that's a good question. So when the superscript is 0, we're just talking about the inputs. But when it's not 0, we're talking about the things coming out of the layer. So these are the things that come out of layer L-1.
Okay.
Okay. So so what we're trying to do here is these are the inputs to layer L. It's a vector of those, and it's by node. So this is the first node, second node, up to DL node. Notice that there's nothing here for the bias, but that's because the bias node doesn't have an input. But the bias node does have an output. So this is for the bias in layer L-1, and it goes up to the number of nodes in layer L-1. And what we're basically going to do is a matrix multiplication to transform from the outputs of the previous layer to the inputs of the next layer. And so we define this matrix WL, and WL connects layer L minus 1 to layer L. So its IJ entry is this weight. So that's a nice way to do it, because it's very intuitive, right? So entry IJ is the weight that connects node I on the left to node J on the right. And so the dimensions here end up being this. So this is the number of, you have a 1 for the bias, and then you have this many non-biased nodes on the left, and then you have this many nodes on the right. But to make the dimensions match up, you have to take the transpose, because this thing is dimension 1 plus d L minus 1. And so you have to apply this t here just so everything works out. But you get this equation. So this is how you get the input to the next layer from the output of the previous layer. Okay. So we said this neural networks have a lot of parameters, but we're still going to call the set of parameters W bar. But now W bar is pretty huge. It's the transition matrix from the input layer to the first layer, from the first layer to the second layer, and all the way to the L minus 1 to the output layer. So the actual number of parameters can be pretty big. This is just an example. So suppose there is you have 5-dimensional input. This really 4 variables and plus the bias, and then you have 4 non-bias, 1 bias here, and then you have 5. I think it's 4 non-bias and 1 bias. I'm just trying to connect this with the code, with like the sklearn code. I think that's the way the sklearn code works too. And in the output layer, the way the diagram is drawn, there is a single output node, and notice that there's no bias here on the last layer, and so this DL is usually 1. So we'll just leave it like that for now. You could actually have several output nodes if you wanted to. You might do that if you want to do like multi-class classification, for example. But this is complicated enough without that. So the number of nodes in the last layer is usually just 1. Okay. So all right. So the neural network is it's just like it's sort of like the dot product that we've been doing for a long time with the linear models. Of course, it's more complicated because it goes layer by layer and it has lots more weights. But it goes in sort of two directions. So forward propagation is you put input into the neural network and then some output comes out. So here's the input, and then this goes into the neural network, and then boop 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 boop, a bunch of stuff happens, and on the other side, h of x bar should come out, where the hypothesis depends on the weight vector, which is all of the weights in the entire network. So how do you do that part? You get from the input to the output. That algorithm is called forward propagation. And you have to do this in order for the machine to make a prediction. And we'll see that it's also used in the training process. Okay, so we're going to go layer by layer. So x bar 0 is just the input, and it also has a bias node. So now there's sort of these recurrences that explain how to get from the previous layer to the next layer. So how do you get from, remember what this is, these are the SL is the inputs to layer L. And XL is the outputs from layer L. And So to get from the inputs to the outputs, remember this thing, the bias node does not have an input. But the bias node should have an output. So that's why this 1 is here. So the bias node will have an output, which will be this 1, but it doesn't have an input. So to get the output for all of the non-bias nodes, you just apply the activation function to the inputs. And this is like a NumPy broadcast operation, because this is a vector, and this is like a real valued function, which is just hyperbolic tangent. So what this is saying is apply this function to every entry in this vector. So what you're going to get is actually a whole bunch of values, 0.1, 0.2, 0.3, etc. Even though the notation is nice and compact, and because of the way the NumPy broadcast operations work, the code will be almost exactly like this. Yeah, so here it's writing out explicitly. So when we use the notation theta of a vector, what we mean is theta of every entry. And remember, we also have a way to get SL. So now we can sort of do everything. We can push information all the way through the network just by using XL and SL. So here's the input to the network, and then you multiply by W1 transpose to get S1, and then you apply theta and add a bias, and that gives you the output of the first layer. And then you apply W2 transpose, and that gives you the input to the second layer. And then you apply the activation function, and that gives you the output of the second layer. And this keeps going all the way until this is the input to the last layer. And then whether or not you apply the activation function on the last layer depends on whether you're doing regression or classification. If you're doing classification, then you apply the activation function one more time. But if you're doing regression, then you would just, skip that step. And that will be the output. So even though all the notation and everything is a little bit complicated, the algorithm, once you have that notation, is really simple. Yeah, and this is, yeah, okay, let's skip that. So here's the pseudocode from the book, and I copied it. It's a little bit misleading. There's like a, if you actually do this, but let's just go through it, and then I'll complain a little bit about something that gets tricky when you actually try to implement it. So now we're gonna follow this algorithm. This is called the forward propagation algorithm to go from the input to the output. So initially, x0 is just the input to the neural network. So this is like a single instance going in. And then as the layers go from 1 to the last layer, SL is this. So you go from x0 to S1, for example. And then once you have the inputs, you go to the outputs of that layer. It's just 1, that's the output of the bias. And then remember, this is broadcast notation, and it gives you like a vector of output values. And then finally, you just return XL, which is the output from the very last layer. So when you actually implement this, the thing that can be a little bit tricky is that this pseudocode gives a bias to the very last layer. So remember, the last layer, you have like a 1 here, and then you have theta. Let's say this is the second to last layer. And then this feeds into the very last layer, which has 1 node and no bias. Okay, so this is supposed to be layer L. So there's no bias node here. So I suggest, instead of following the pseudocode exactly, you go up to L-1 and then do the very last layer as a special case. So that's a good idea, because in the last layer, you don't want that bias output there, because there's just the output from the node, no bias output. And another reason is then you can handle the question of whether you're doing regression or classification. Because if you're doing classification, then you want put the theta there. If you're doing regression, then you want this just to sort of do nothing and be the identity function. So you can make that choice if you do the last layer as a special case. So and we'll actually go over the pseudo code for this. In fact, I think we can maybe take an advanced peek at that right now. So I think this is here. So here's an implementation of a neural network, and this will be the basis for your code when you implement it. By the way, if you want to totally ignore this structure here and just try to implement it completely on your own, that's fine too. So here the input is x, which is a vector, which is the just the inputs, and w, remember, is huge because w is a vector of matrices. So here we decide on the activation function, and here's just some error checking. Make sure that the input has a bias node, and it helps just to, when you're debugging things, just to make sure that the sizes match up. Okay, so what this is going to do is it's going to go through it and it's going to compute. Maybe I should use my pen to make a note here. If I can get this to work. So what this will do is it will record XL for each L equals 0, 1, 2, up to L. So it turns out that you're going to need those later, possibly, if you're doing back propagation. And also you're going to need these S's. So when we talk about back propagation, you're going to need those S's to make it work. So you also want to record or remember SL for L equals 1 to blah, 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 L. Okay. All right. And so what this is doing is it's just adding x0 to the x bar 0 to this list that's going to record all of the things. So now we go over every matrix W except for the very last one. And I left this for you to do, but just in mathematical notation, S is going to be equal to WL transpose times x bar L minus 1. And you also have to update XX. So you want to add in the value for XL, which is 1 stacked on top of theta applied to the thing that you just computed here, which is SL. Okay. All right, and then you just increment L. And now this is doing the last layer as a special case, like I was suggesting when we talked about the pseudocode. So you need to do something here to update the last S. And then if you're doing regression, then it's going to be what if you're doing regression, then the very last output XL is just going to be there's not going to be a theta applied. Whoops, oh my gosh. I just made everything jump around. That's unfortunate. But anyway, so if you're, what am I doing here? Give me back the mouse. Maybe I can kind of fix this. Okay, anyway, sorry about that. So if you're doing regression, then you just put in SL. So the output is the same as the inputs. But if you're doing classification, then it's gonna be theta. of SL. Okay, so you do two cases there, and then you return. And that's the forward propagation algorithm, which is sort of like half of everything you need to know about neural networks. So any questions? Any questions about that? Okay, so I'm going to now explain the back propagation algorithm, and I'm going to need to come back to the notebook and start on some fresh paper here. So back propagation. So back propagation is the algorithm that trains neural networks. Propagation. Okay. And so the basic idea, you have a neural network. Here's the output, and then in the previous layers, you have a bunch of nodes, and then in the previous layer, you have even more nodes, all the way back, etc., to the initial inputs. So here's 1, x1, x2, x3, and then lots of things coming out here. So the basic idea is kind of like a stochastic gradient descent. So you're going to put in an instance from your training set, and it's going to sort of push forward, and then you're going to remember all the x's and s's that we just talked about. So once you've pushed it forward, you can compare what came out to the training y. So that will give you an idea of how wrong the output is, and this will let you estimate sort of the gradient for this one particular training point. So in order to compute this thing, so remember this is with respect to the entire parameter vector. Instead of just trying to compute it all at once, we're going to compute it layer by layer. So this will be sort of like the derivative of this particular training instance with this layer. So this will be sort of like, first we'll compute that, and then based on that, we'll compute the derivative of the error for this particular instance with respect to L minus 1, blah, 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 and it'll sort of go all the way back, and then we'll get this for the very first layer. So these things together sort of are the gradient, the pointwise gradient. You can get the pointwise gradient for the entire parameter vector. It's just the list of these derivatives for these matrices. So we'll give more details about that in just a second. But this is basically how it works. So you put one training instance in, and then that's forward propagation, and then back propagation comes back, and it computes all of these values. And then you do sort of like a gradient descent the way you're used to it. So W becomes equal to W minus the gradient with respect to the pointwise error times some learning rate. And so you just do this many times, and it's stochastic gradient descent because you do it instance by instance. And that's how you train the neural network. So let's start. So we're going to have to take, this is just a really abstract algorithm that we just outlined. We will have to take some actual derivatives. So maybe in case people are not super familiar with hyperbolic tangent, hyperbolic tangent is equal to, well, I should put in the input variable. So let's just use like a single variable x here. So you might have learned in calculus that this is the same thing as hyperbolic sine over hyperbolic cosine. And what these things are is e to the x minus e to the minus x over 2. That's hyperbolic sine. And hyperbolic cosine is e to the x plus e to the minus x over 2. So the over 2 part cancels, and you can just think of hyperbolic tangent as being the ratio of these things. So the easiest way to take this derivative is just to use the quotient rule. It turns out that the derivative of hyperbolic sine is equal to hyperbolic cosine, and the derivative of hyperbolic cosine is equal to hyperbolic sine. So if you compute the derivative of hyperbolic tangent, just using the quotient rule, it becomes hyperbolic cosine squared minus hyperbolic sine divided by hyperbolic cosine squared. And then if you split this fraction apart, it's equal to 1 minus hyperbolic sine squared over hyperbolic cosine squared. But notice that that is just 1 minus tan h squared. So this is a nice property of the activation function hyperbolic tangent, that its derivative is expressible in terms of itself. So we'll see that works very nicely when you use it for backpropagation. So backpropagation is very general, and it can work for different activation functions, or even for combinations of different activation functions. But we're just going to give the version that works with the activation function hyperbolic tangent. Okay. All right. So let's do an exercise from the book. Suppose that we just have a simple perceptron with hyperbolic tangent as the activation function. So we don't really have a name for this, but you might call it just like a soft perceptron or something. So you have the bias input x1, x2, x3, and then these are all going into the activation function, which is hyperbolic tangent. And you have these weights. So this is like W0, W1, W2, W3. And here's the output, which is basically just the, this is hyperbolic tangent of the dot product of W and X. So what would be the error here for well, okay. So the error, if you use just mean squared error, so this would be the average squared residuals. So the differences between the predictions and the actual values. So here's WT times xn. N is ranging from 1 to capital N, which is the number of instances. So you take the difference between the prediction and the training label, and then you square it. So this is just the average of the squared errors, in other words, mean squared error. So what if you were to take the gradient of this thing just in this simpler case? So this is the gradient over W, and now W is just what we normally think of it as a simple parameter vector. So the gradient comes all the way inside the sum, and it makes this 2 come down, kind of like in just the usual derivative sort of way. So you get 2 times tan h wt xn minus yn. Now, by the chain rule, you have to multiply times the gradient of the inside here. So the gradient of yn has nothing to do with W, so its gradient is just 0. And for this thing, you have 1 minus hyperbolic tangent squared of wtx. So that's the derivative that we just derived. And now finally you multiply by the gradient of this thing. And the gradient of a vector times x is just x. Okay. So this is that wasn't easy. If you haven't done calculus in a little while, especially, but that's kind of as easy as it gets, and it gives some kind of like
why did you times x bar again?
So what I wrote there is it's just continuing to use the chain rule. I want to multiply by the derivative of this part, but we're not really doing the derivative. We're doing the gradient. So so what I have to do is take the gradient with respect to w of wtx. And so we wrote down a formula for this a long time ago. It just happens that this is equal to w. You can see why it's true if you write it out. So it's like wi times xi. So if you take the derivative of this with respect to like wj, this is just xj. So when you take the gradient, you do this for j equals 0, 1, 2, 3. And so what the gradient ends up being is x0, x1, x2, xd, which is just x. So I know that was kind of fast, but I can give you a reference to this later if you want. This is one of the two formulas that we've been using a lot during the course to do the gradient. One of them is that if you take the gradient with respect to some vector, and then you have a dot product, then the answer is just the other vector. So we've kind of been using that as a formula, and I can prove it later on Piazza more slowly if you want me to.
Yeah, that makes sense. Thank you.
Okay. All right. So that is a little bit of a warm up. So with a full neural network, you have W equals W1. So this is the transition matrix. W2 all the way to WL. Okay. And so now consider this En is the notation that we use for the error on a single point. So this will be like, here's the whole big neural network, which depends on the choice of weights. And then you put the input into it. And, sorry. So this is the nth input. And you take the difference between that and the nth label, and you square it. So this is the pointwise error. So this is the error that accrues to like a single training instance, which is just the nth training instance. So when you're doing mean squared error and most other kinds of error, mean squared error, this would be En, it's just the average of the pointwise errors. So it's 1 over n, and then you put En here. So this is for the full neural network, as n goes from 1 up to n. So what you can do is, it's hard to start thinking about what the gradient of En is, but when you take the gradient of this big error function, whatever it is, the gradient just comes inside. So this will just be the average of the gradients for the instances. Okay, so now we have sort of a simpler problem. So instead of wanting to know the gradient of the whole big error function, we can just do the gradient of this simpler thing. And what's more, so you want to know the gradient with respect to W of En. So another way of thinking of that is, W is this. So this is going to use some sort of matrix calculus notation, which I'll explain in a second. So this is, and I'm going to drop the subscript E here because it just makes things a little bit too busy. But this is just the pointwise error of some point. So if you take those are supposed to be partial derivative symbols, not twos. They do tend to look like twos when I draw them. I'm sorry. So this will be the derivative with respect to the first weight matrix. This will be the derivative with respect to the second weight matrix. All the way out to the derivative with respect to the final transition matrix. And each one of these, so remember, like, let's just consider, I don't know, WL. Remember, this is, the dimensions are 1 plus DL minus 1 times DL. That's because it goes from outputs of layer L minus 1 to inputs of layer L. So all of these are these same dimensions. So, this thing, the dimensions of this are 1 plus D1 times D2. So I write this as if it's just a number, but it's not actually a number, it's a matrix. And the sort of the ijth entry of this matrix is the partial derivative of the pointwise error function with respect to the ijth entry of the matrix W2. So this would be an actual number. And so this is a matrix of those numbers. So I hope that makes sense. So each one of these is a little matrix, which is the same dimensions as the corresponding matrix here, and it just shows like how the error changes as each weight changes, basically. So that's what this should tell us. It's how does the error change as each weight changes a little bit. And that's exactly what this conveys also. It's just, instead of lining up all the parameters in one flat line, it's got them arranged in matrices, which is going to be a little bit more convenient to work with. Okay. All right. So now we're going to start outlining how backpropagation works. So backpropagation works in time big O of Q, where Q is equal to the number of weights, which is pretty fast. We'll if we get there, we'll do an example by hand for a fairly large network. Okay, so the sort of key insight here that makes this whole thing possible is this idea of something called the sensitivity vector, which is denoted by delta. It's a vector, so I put a bar on top. And each layer has a sensitivity vector. And what this is it's supposed to be sort of the sensitivity of the entire output to changes in the inputs to the layer L. So I'll write it like this. So this is how the pointwise error changes as the inputs to layer L change. So they call it the sensitivity vector. And it's supposed to express how sensitive the overall pointwise error is to changes in the inputs to layer L. Okay. So as we go along here and we give the basic algorithm for for backpropagation, there are a couple of important formulas that I am basically not going to justify that you can derive using calculus. And the derivation is in the book. For most people, a lot of people just haven't had the prerequisites, and this stuff is complicated enough without doing the full derivation. So so it turns out that, you know, this is one of the things that we want. In fact, because this L here is kind of is arbitrary, this is, if we can just come up with a nice expression for this, we've sort of solved the entire problem. So we know how to compute the gradient then, and we can do gradient descent and train the network. And it turns out that this thing is equal to WL minus 1. So these are the inputs into layer L times the sensitivity of layer L. So that makes intuitive sense. It's kind of saying that that the way the output depends on the transition matrix from layer L minus 1 to layer L is just sort of the magnitude of the outputs from layer L minus 1 times the sensitivity of layer L. So, and of course you can do calculus and derive everything exactly. But this is a crucial equation for backpropagation, because it says that now we would be done with the entire problem if we just knew how to compute delta L. So here's the formula for computing delta L, but this this formula is a good definition, but it's not a practical way to compute what delta L actually is. So for that, computing delta L, it turns out that you can recursively compute these things backwards. So if you can figure out what delta L is in the very last layer, which you can actually do the very last layer just from the definition, as we will in a second. But once you know delta L at the very last layer, which you can get from the definition, there's a way to use that to compute delta L minus 1, and you can go all the way back to the sensitivity vector of the very first layer, delta 1. And once you have that, you have kind of figured everything out, because now you use this to compute that, and then you use these to build up the gradient, and then you do gradient descent. Okay, so how does this recurrence relation between these deltas work? So this is the second crucial formula, which I am also not going to justify here. So it turns out that the recurrence relation between the sensitivity vectors is this is the derivative of okay. So when I write that, what I mean is this is like the derivative of theta of SL, where the variable is also SL. So in other words, this is just a calculus 1 problem. In fact, you can just write down exactly what this is. This is 1 minus theta squared SL. Okay. There's more to this formula, so let me write the other parts too. So now we have this funny symbol, this X-man symbol. What that is just broadcast multiplication. You know, like in NumPy, if you multiply a vector by a scalar, it just automatically transfers to it does sort of multiplication entry by entry respectively. So what we're doing here is this is going to be a vector, because we're using broadcast notation here, and then this scalar minus a vector is going to be a vector. You know, even this little thing is using a little bit of broadcast notation, because this one, it should actually sort of, you know, be np.1s or something. So we're going to take 1 away from every coordinate. So this is coordinate-wise multiplication. And what we have here is WL plus 1 times delta L plus 1. Okay. So here we have a little bit of a dimensionality problem, because the dimension here is going to be dl. So this is a vector with that's dl rows in one column. But if you figure out what this product is, this product turns out to be, let's see. So this thing is dl, dl period plus 1 times dl plus 1. And this thing is dl plus 1 by 1. Okay, so these match up. And so the product will have the dimensions dl plus 1 times 1. Okay, so you can't actually do, I mean, so this is not making a lot of sense, because the thing on the left is shorter than the thing on the right. It has like, you could also think of this as being times 1 here. Okay, so there's this plus 1 problem. Where that's coming from is it's the bias. And so when you go backwards, this is like it's sort of trying to assign blame to the bias. But the way you solve this problem is you just ignore the entry that corresponds to the bias node. So the notation that the book uses for this is it goes from 1 to dl. Okay, so that's the book notation. What it means in practice is that this is going to be some vector like a, b, c, and we're just going to ignore the top one. So there's also Python array slicing notation for the same idea. But this is just saying that we're going to ignore the top one. And I know this is a little bit of a mouthful. So let's try to write, we're not going to derive it, but let's write down something that will kind of help us make sense of it. So this is sort of the slope of the activation function. So that is what this quantity is, times the size of weights connecting the next layer. And that's what this W is, times the sensitivity of the next layer. Okay. So just as a description of what the sensitivity at layer L should be, this kind of makes sense, because so it's saying the sensitivity at layer L should be proportional to the slope of the activation function. So that's sort of like you know, how the outputs are changing as the weights change a little bit. And then if you get bigger weights, this should make the sensitivity more. And if the next layer is more sensitive, then the current layer should up the sensitivity of the current layer. So this is how the sensitivity of the current layer depends on the sensitivity of the subsequent layer. Okay, so all right. So we've kind of like we've done it all, even if this seems kind of incomprehensible right now. We have to talk about how to do the base case to get the entire thing started. So we need the sensitivity layer, sensitivity vector of the very last layer. So to do this, you can use the definition. So this is the partial derivative of the error with respect to SL. So the one way to write what the pointwise error is, and this depends on whether you're doing regression or classification, but let's assume it's classification. So that means that the activation function is applied on the very last layer. And so the output of the entire network will just be the activation function applied to the inputs to the last layer. And then this is, I'm dropping the N subscript, but this is just the true label of the example that we're talking about. Okay, and this will be squared. Okay, so what this is saying is that I should just take the derivative of that where SL is the variable. Well, that's no problem. That's just equal to the 2 comes down. This is just like our simple perceptron example again. So 2 comes down, and this is theta L minus Y times 1 minus theta. So this assumes now that hyperbolic tangent is the activation function. If it's not the activation function, then the formula will be different. But also, this is the only place where the activation function actually comes in to the formula. So it's really easy to swap out activation functions. You just have to change this a little bit. Okay, and okay, whoops. All right, so we can go even further here because XL, which is the output in the very last layer, is actually equal to theta of SL by definition. So that's how you get to the very last output. So we can rewrite this as it's 2 times XL, which is just the output of the entire process, minus Y, times 1 minus XL respective multiplication XL. And the output of the final layer should just be a scalar. So this will just be ordinary multiplication if you have only one output node. Okay, whew. So that's if you're doing classification. If you're doing regression, what this part is you know, the derivative of, so this is theta prime of S bar L, which we also needed in a different part of the process. So you can also use this expression there. But if you're doing regression, then theta is just the identity function. So it's the function that does nothing because you're basically not applying it. And in that case, theta prime is just 1. So if you're doing regression, then delta L is just equal to 2 times X bar L minus Y, period. So this is in the case of regression. And this is in the case of classification. All right. So I know that was a lot. Let's go look at the code here for backpropagation. All right. So here, this is just this. What is it getting? It's getting an instance. Oh wait, sorry. It is getting an instance, but this XX, this is the output of the forward propagation, because to do backpropagation, you need all of the X's and all of the S's, right? But actually, you can cache out all of the S's for X's because of tricks like the one that we just did. Let me come back.
Flash drive.
Here. So everywhere there's an S, the S is always inside.
Selecting this, and it's still selecting that.
It's always inside of theta, and so it just turns into an X. So, you know, in theory, you need all of the S's and all of the X's, but if you're using a hyperbolic tangent activation function, then you just need the X's. So here, we get all of the X's that were discovered during forward propagation. This is the parameter vector, And this is the true label for the instance that we're actually working with. So now, depending on whether you're doing regression or classification, you initialize delta differently. That's what we were talking about here in this very last part. So this is the initialization stage. If you're doing regression, then delta should be that. If you're doing classification, then delta should be that. And come back here. So now you just you go through, and what this stuff is talking about here is, so remember this formula. Delta L is equal to theta prime SL times W L plus 1 delta L plus 1 from 1 to DL. So that's what's being computed here. So first you need theta prime, and this is like 1 minus XL times XL. If you're using the hyperbolic tangent activation function, and now you compute. So this is just the delta from the previous layer, which you need right there. And now you have to compute delta L. So to do that, you just do this multiplication. You have this, you multiply in W times that quantity, and then do the respective multiplication. And then you remember that because you need the list of all the deltas to finally compute all of the gradients. Okay, so now you have a list of all the deltas, you send it back. And now to compute the gradient, you do so in this function here, and we've talked about this before. What this is computing is dE dWL. This is equal to XL minus 1 times delta L transpose. Okay, so that's the thing that's missing here, is just this dot product here. And now you have a gradient, which is just a vector of all of these things. So you return that, and then you can do stochastic gradient descent. So this is just ordinary stochastic gradient descent, and then and that's pretty much it. So when you update the gradient here in this version of gradient descent, you do it for each matrix. So what this is doing is it's doing it for each of the transition matrices. Okay. Yeah. So that's it. So I was kind of hurrying there at the end to get it all in, and I have an example, a worked example, which I guess I'll just go through here. There's also a worked example in the book. So it's not going to make sense until you do it by hand a couple of times. It's really complicated process. By the way, I accidentally scanned this middle page twice. So we might go over. We will look at this again on Tuesday next week. But if you want to do an example by hand, you can try to follow along here. And there's also an example worked by hand in the book. And just to give a brief, I should shut up now, but to give a brief preview of what we'll talk about last week, notice that, so here you have the way that the gradient for the first transition matrix, the values are pretty big here for the last transition matrix and for the second transition matrix. But by the time you get back to the first layer, these values are tiny. And so what happens is that the first layer, those weights don't get updated as effectively as the last layer, and it's very hard. Like the different layers learn at different rates, basically, and that makes training deep neural networks very difficult. So next time we'll spend just a couple seconds talking about deep neural networks and some tricks that can stop this from happening. This is called the vanishing gradient problem. So we're a little bit behind. I'm gonna stop this, and I'm not gonna